this time with a lot of connections and some cool stories. After we do the geometry of potential potential and force formula or laws, and consider just the mechanics of a single ball bounce for a couple of cases. Constant force, and this is relevant for speaking of YouTube, crazy daredevils that dive 80 feet into a kiddie pool. We'll look at the energetics and health risks of that particular activity. Then a linear force, quadratic potential, will show up here that that's very much like a balloon. And then the general nonlinear force, and this is a super ball floor. Or if you're talking about something that's a little faster, high chromium steel ball bearings on a high quality anvil has a coefficient restitution approaching 99%. So if we ever wanted to build a really good one of these demonstrations that made a nice clicking, ringing sound, that would be a good way to start. The geometry of potential dynamics, just for two balls, brings up our favorite toy, but I want to make a parable here in which I have an allegory for Los Alamos, which I'll call Rump Company, and I'll explain that, and then its competitor, Livermore Laboratories. And while I'm showing you this, we'll be talking about all of the results of thinking about potential and force-driven dynamics, which is the solutions that we can do very easily on a computer that we have idealized so that the geometry works. Then I want to tell you in detail an interesting story of the Super Ball project, Project Ball at the University of Southern California, when I taught my first, shall I say, college physics, but it was a little higher level than that at the time. All pre-meds and dentals had to take a pretty hard course. And we went down and visited the Whammo Manufacturing Company, which is the inventor of hula hoops and other things, but we were interested in the Super Bowl at the time, obviously. Go into this. This is an allegory of all research, this particular story. And then we'll finish up with some real quick looks at analogies between a shock wave and acoustical horns. And there'll be a little problem I'll give you to take with you. And then the final story will be about a very colorful character called Sterling Colgate. Colgate of the Palmolive Colgate fortune. And I've gotten a lot of stuff off the web on him that you might find interesting, plus a few stories that aren't on the web that are a little bit colorful. We may have to stop the video for that. But anyway, and then many body collisions that involve the western buckboard, the bouncing columns of Newton's cradle. We've already talked a little bit about that. I want to review that. And then zigzag geometry for various kinds of crashes on the freeway. We'll go through that rather quickly. These are inelastic cases. And then there's the superelastic model for rocket science. So we got a lot to do today, and we'll keep the duty roster up there on the far right to see how we're going through this. This is the Thales geometry associated with the potential and force law that you would get for any spherical object, but in particular a super ball doesn't like to be crushed. This little distance right here with a dashed line on it indicates where the ball would have been if it hadn't gotten flattened by hitting or being pushed upon. And the result is to have a force, which is drawn in the simulations as an arrow upward when we're shooting upward, that is the force as a function of distance. And the idea is to figure out what that force is. Now the picture that I've drawn here is a detailed geometry of one of the oldest theorems. This goes back to Thales of Miletus, which is now in Turkey, but it's across the Aegean Sea from Athens. And so at the time of 600 BC, it was something of a center of learning, and Thales was the first human to predict an eclipse. And if you realize that all of the things about astronomy were a superstition at the time, he really scared a lot of people when he could do that. He became almost godlike for that. But he's also an expert in what we now call geometry. And this is 600 BC, 300 years before Euclid starts to put all this stuff together in a kind of book that we're used to reading now. The Elements of Geometry was his famous book. So this is really the beginning of critical thinking, if you were, in scientific and mathematical thinking. So we're using that, and the idea is that the Thales theorem is that a diameter always subtends a right angle with a circular arc. Here we have two of them right next to each other, showing that a rectangle has been inscribed, and that makes the theorem somewhat trivial. Trivial in the sense that you use symmetry to see that indeed they are right angles. And if they are right angles, then this little triangle here is similar to this bigger one here, and that leads to the fact that x is to r, as r is the 2r minus x. So r squared is the 2r minus x. Yeah.
Which two triangles are you considering here?
The first one, which I'll point with something that's a little sharper than my finger. The first triangle that I'm looking at is one that has x on this side, and that's the depression that we're interested in. That's the independent variable for the force law. And then we'll be seeing a radius of some kind of the circle that that's where this ball has been crushed. And then that triangle right there is similar to this triangle right here. Okay? So the idea is that x divided by r is the same, equal to this r divided by 2r minus x. Okay? So we have x over r. Let's go ahead and write Thales' equation. If you could write equation, you've got to realize algebra didn't exist then, so we're already doing something that's well beyond 600 BC. But the 2r minus x is the other side, the big side of the big triangle. So once again, similar triangles is making all of the physics and the mathematics of it right here. Okay, so that then gives you an equation for r. You can go x times 2r minus x is equal to r squared, or r is the square root of x and 2r minus x, which is the mean, geometrical mean of these two dimensions. X is depression, and 2r minus x is all the rest. So the idea is r is indeed that, but for x small, as it is for the superball, if you crush it much more than that, you're liable to have it explode on you. It's like nutty putty. It will shatter when it's struck suddenly, and that's a big issue we're going to have down here when we look at this project ball, how it all evolved. But 2rx, ignore the x squared, is called the sagittal approximation. And that's what we're going to use to figure out things. Now, how did we stumble into that? That's the story in the middle of this lecture. But you can see that this force could also be given if you knew what the pressure of the ball was, and the area of the depression or flatness, the flat part of the thing, that is pi r squared, is the area that this thing is actually making on the floor or the wall it is hitting, times the pressure, and then r squared being 2rx, okay? We've got a force law, a force that gives you a constant, this thing right here, 2 pi r, and the pressure, and then the pressure, okay? So that's a Hooke's law. That's very different from the super ball. Very simple. This is the Hooke spring constant that we're talking about right here, K. And the force is Kx, actually minus Kx, if you were saying x is this way, then the force is opposite to it, trying to get the ball back out of the floor. So far, so good. But the super ball is weird. The super ball is a whole volume, and crushing that much material, depending on how you crush it, rapidly or not, it's going to depend on the bulk volume modulus. Now, if it is linear in that, you get a force law that's a little bit different from this. Now, we have to figure out what the volume is that you've crushed this thing to. So I'm doing the integral of the area pi r squared with respect to x, and writing that as a function of x. So you get a, without the approximation, two terms, 2 pi r x dx, and then you get x squared dx, so you get a cubic from that, and you get a quadratic from that. So that's the exact value for the volume that has now been taken away from the super ball, crushed as it were. And for, you check this thing, for x much less than r, this would correspond to just r pi x squared. But for x equal to 2r, if I push the thing and crush it to nothing, I've eaten its whole volume, which is 4/3 pi r cubed. So those are the two extremes for this answer here, ignoring this if x is small and then putting it together with x equal to 2r exactly, not ignoring this, we would get 4/3 pi r cubed. So those are the range of this thing. And I also point out, as we'll bring up later on, and this was something we discovered in the process of doing Project Ball, which is written up in an article that I will also show, because I finally got a copy of it that's worthwhile on the thing. And as I say here, ahead on, and I forgot to put the page, it's down around page 50 of this lecture. So this is a function of velocity as well. Okay, now what we're going to look at here is an animation, and I guess we'll have a contest between the old, which is what this is, and TC will put up the latest one. I'm going to try to run the old one on this machine. It's the only machine here that right now is hooked up that can run this. So I will back off here from this and go over to there. And what we're looking at, what we're going to look at is, and you might show, and you've already got it up there, the menu that replaces what's in this old one. And I'm going to go ahead. Got to move this thing down. It's not so easy to move things around here. I'm going to plot a with a gravity potential, we're going to be dropping this ball now with gravity and a nonlinear force. So that's what I've got. Okay, now this thing runs pretty fast. I'm going to stop it for a minute and make it a little bigger. I just do that by dragging this thing over and then dragging laboriously the frame over, and it doesn't have the quick action that you get with a modern thing like the HTML that TC has put together. But let me just go ahead and then I'll slow the motion down a little bit to something that just creeps along. Maybe I'll make it even a little less than that if I can. But there's something else I can do with this one I don't think I was able to do on the modern one, and that is grab the energy and just change it. So I'm going to bring it so that I take up the whole frame with my motion. Did you have a way of getting that particular? That's one we make a note. It's worthwhile doing because we need to do that for the quantum things. You can just grab the ball though. You've got it so you can grab the ball and bring it to a lower level.
You drag it and release it, actually change the velocity.
Actually, you have to. Yeah, now you made it bigger. You gotta give it some lesser energy. Anyway, this one is just bouncing along with no friction. We turn the friction off, but we do have the gravity on, and you can see that right here. The potential energy is indicated by the green curve here. The force is indicated by the yellow line on this graph. It's a little more visible. DC has taken care to make a more visible thing for the simulations you guys have access to. I'm not even sure if this yellow is going to show up on the camera. I don't know if you can see. Does it show up at all?
Yes.
It picks up yellow. That's good to know. Because we've got a lot of yellow in this course.
Barely.
Anyway, there's the force vector acting on the ball. And you can see a little force vector inside here, and you can also see it on the new one. In your case, you might make a note of that the force vector is sitting right on the line of the character M. It's a little constant arrow you're pointing at it. Yeah. This one is not too much more visible, but at least it's clear of the character. So what we're getting here is the force on gravity, which is always acting, and then the force by the floor, which expands to a maximum value as the ball is deeply embedded, or I should say flattened, by the floor. So I'll try to stop mine at that point.
Dr. Harter?
There we go. I just caught it right on the maximum.
Dr. Harter?
And you look like you got yours fairly close. Yeah.
So when the ball hits the floor, it bounces back.
Right.
Which means the floor exerts a force, an upward force on the ball.
Which is what you're seeing right now. That's
so
the biggest.
That magnitude of that force is equal to mg, right? Or is it something? Is there some other force else?
Mg is constant throughout this thing. There's nothing that ever changes with that. This part is always being attached to the force generated by the ball being crushed. So
you can see the magnitude of the gravitation right here, and it's quite a bit smaller at this instant.
Yeah, and the same thing here.
Floor's force.
So
Same thing here.
There are some other forces which contribute to the upward force acting on the ball. So what?
I guess I missed that question.
No, what are the forces which contribute to that upward force, Dr. Harter, once the ball bounces back?
All we've got is a gravitational force that's constant and downward, and every once in a while when we touch the floor or get buried in the floor, we get a variable force, a force that's just a function of how far I buried. Let's call it X or Y. and it's nonlinear, as you can see from this curve here. It's nonlinear. We'll talk about very nonlinear, in fact. We'll talk about the balloon force where it's quadratic. We'll talk about the linear, and we'll talk about the just a simple volume force where it would be quadratic. Those are the three cases we're due here, and the third one is the weird one. That's the super ball. Super ball has a little bit extra to offer because it's kind of like nutty putty. When you push it, it blow back. There's a name for that, thixotropic or something. I forget what it is that we name forces like nutty putty. Nutty putty's a famous toy, right? You get a lump of it and it just settles down in like a liquid. But you roll it up real quick and drop it, and it bounces like a super ball. Has a tremendous coefficient of restitution. You ever played with that stuff?
I wish they have a sample.
Yeah, they must have it in India.
Yeah, must.
It's
Not sure, I don't remember it.
yeah, it's very strange stuff. And super ball is strange too. It's just it doesn't show it at first. So I want to go through each of these cases real quickly here to get you familiar with all of the possible complexity of doing the super ball bounce single ball correctly with none of this ruler and compass stuff anymore. This is something that has to be solved numerically. Analytic solutions for most of the cases are not available. You'll see an old version of the menu here. I haven't replaced it with a new one in the talk. I'll make sure we do that. It's not too different.
No, it's very similar. Self-explanatory.
Yeah, you search the box is the same. It's just got more writing and discussion than it had last year. Okay. When you want to change the force law exponent, you do it here. You want to make some more gravity, you do it here. Want to throw in a little friction to make it more realistic, you do it there. And we'll be talking about more balls that do this later on. Want to change the force constant that goes in front of the power law, you do it there. I don't think there's anything else I need to discuss right now. But this is a little different from the simulations we've done before because it draws this potential force diagram with everything on it. We need to explain that a little bit more. First of all, this little triangle here, that's this thing right here. Now, this diagram should be turned over, if I'm not mistaken. No, it shouldn't. It's the way it should be. The force over 1 is equal to the slope of the potential curve, which is delta U divided by delta X. Well, it's really the derivative of U with respect to X, but we're looking at it as a finite triangle that you can actually see. And so as this thing moves, and let's take this case over here, or on TC's screen there. We'll try to do them the same. What you're seeing is that the number 1, whatever that is, that number 1 never changes. And that's what makes it geometry, you see. And then the force itself, you see, this thing right here, when it gets pointing the other way, it turns you can see the base of this thing is the force. And as that moves, this is the geometry that is following throughout. So you see this, the hypotenuse of the triangle turning around, and it's always normal. That's kind of a little unusual thing, but that's what it's doing. It's tracking the slope that determines this relationship between force and potential. So it is normal to the potential curve in this weird space where we pick this unit here and then let that scale the force. So it starts out with gravity pulling a thing this way, and that's constant until it goes inside the ball. Then it slowly grows, it's nonlinear, and once it grows significantly, as you can see, the force value, that yellow line right there, indicates the value that the force has. Here, the magnitude of that yellow thing is the same as that thing. And then it grows and changes sign. Right here, it's negative. This yellow line is an arrow pointing down. And then at some point, it becomes 0 and changes sign. Now, is that you have a slow view going, I can't make this one any slower without stopping it, but yours is very nice and delicate, and you can see these things all happening very slowly. And this is what you get to play with if you want to study this for different situations. And we'll be using this kind of picture throughout the course for other types of potentials and force laws. Okay, so far, makes sense? More geometry than you can do with a ruler and compass. Unless somebody gives you the curves.
This differential triangle is elemental.
Yeah, that's very elemental. Yeah. Okay. Well, this is an interesting stopping point right here. This is where this potential due to gravity plus the ball, and the ball doesn't turn on until here, or to the left of here. But as soon as it does turn on, it can finally get to the point where it's pointing up with exactly as much magnitude as the gravity was pointing down. So this is the moment where there is 0 total force. Okay? Well, that better be the minimum point for the potential, where the derivative of the potential is 0. Okay, so the total force is 0. That little red dot that was negative has just come up to 0 at this moment.
I wasn't able to get there. I wasn't able to stop at that precise.
Yeah, it's really hard to stop this fast one, but I'll try to stop it at the bottom. Boom! I missed a little bit. You can see the triangle's just coming on its way back up there. But I just wanted to make sure you saw that point. So this is where the ball would sit if I just let it settle down, reach equilibrium, right? This is an equilibrium ball right there. If I can just get it, everything stopped right there, it'll stay stopped. We have a lot of momentum going in, so we're going to come out. But if I take all the energy away, I can just be there. Now that's one of the advantages of this program right here, is that I can just take the energy down to the bottom, you see. And if I'm close to the bottom, I'll just get, I'll resume it here, I'll just get a little oscillation, right? I'm very close to the bottom there, and so I get a little oscillation around the equilibrium point for this ball. So this is a very soft ball, or very massive super ball. If I were to get a super ball about this big, it would probably sit like that on the floor. And that was one of the reasons we went down to Whammo. We picked up a lot of very weird super balls that day. So the equilibrium point for this thing is right about, let's see if I can get it down there. That's about it right there. Okay, see a little bit of quivering. And you've already got it on there. Is that?
I locked it down.
Oh,
it
you
still
locked
has
it.
an energy
Okay.
that's
Okay.
still provide full motion.
All right, so that's the significance of this, the second interesting point. We're talking about the turning point here on the right side. This is a midpoint, sort of. It's not in the middle, but it's midpoint as far as force goes. And then the next stop is maximum penetration. Now here's where the kinetic energy is zero. Again, we started with it zero here, we end with it here at zero. Those are called classical turning points in quantum mechanics of potentials, right?
So that's a place where there's maximum compression, the ball comes to
This
rest
is
for a
maximum
moment,
compression,
and then bounces back in the opposite direction.
bounces back, and of course from here out it's not compressed at all, unless you could feel the gravity curving on it, right? The gravity is acting with a constant force all the way out. Then the gravity gets turned around by the ball's desire to get the heck out of the floor. Okay, so that's and this is from the program. This is a nicer drawing, obviously. Okay, so you're looking at the program that makes this over there. So floor force is maximum. There it is. That whole force vector right there. Okay, and we're showing actually it at work on the ball from this diagram, where this is a unit, some kind of unit value. Okay. All right. I think that's all we need. This is just a redo of all three of them in the modern setting of the HTML program. Just cut and paste it from the three main points of interest in the dynamics. All right, now, general nonlinear forces, like superball floor, that's what we're dealing with here. Ball starts high, comes down, just barely touches right here, then gets crushed, comes up, just like we've been showing in the movies, okay? And a thing I'm interested in is the amount of work that the various forces are doing. And the idea is that the area here should be the same as the area there. They're very different looking areas here, but that has to be the total potential energy, okay, that you're talking about. You know, by crushing this ball, and the gravity is potential is also lower, so this ball has really got some work done on it. That's what we're talking about here. We're talking about the reverse of this equation. And so that U total from Y max, which is out here, and Y static, okay, that's the area that we were talking about here. And then from Y static to Y max, between these two, is this area, okay? And then that plus whatever it was at the value H. Okay. This, let's see if this is, something's a little screwy here. I'm thinking UH plus the work we put into it should be the same energy as we started with, same total energy. So U of H right there has to, plus these two areas should be equal to U at Y max. It's kind of a neat relation. It's worth studying. Get yourself familiar with everything that's going on here. Okay? And we're talking about the work, energy acquired, area of f of x is minus the potential. So we take the minus sign over here, if you want, and then integrate the potential, or leave the minus sign on U and just integrate the force without a sign. Now, I should also point out another integral that we're going to be interested in. This is an integral of the force as a function of x with respect to x. If the force time dependence is also known, which the computer will give to us, and I integrate f of t with respect to t, that is another name. That's momentum acquired. That's the area of an f of t curve, which I'm not drawing here. But the result will be the momentum gained, and of course you have to put the limits in the right places, just as you do here. But that's just our Newton's equation, right?
The kind that the force doesn't have to be time dependent, right? You can still define impulse for a time independent force where you just multiply the force by the time interval.
Well, up to this point, and probably a little bit beyond, the force is not changing, right? So all during this time, force didn't change. But boy, it makes up for it, right? Boom. So same thing is to be said about its dependence with x, which is what we're plotting here. Which you can see now, if I were to do a time plot, there wasn't any change at first. But we were gaining momentum, right? This acquisition of momentum is occurring here by our, really, it's our only axiom for classical mechanics. This is now stating it in the way that you get it in most texts. Before we were drawing diagrams and velocity plots and Lagrangian plots and Lestrangian plots and all that kind of stuff to make a connection with weird way we do things here. All right. Now, I'd like to discuss the simplest case. You want a constant force? Let's go for it. Okay? Now that means I'm going to have a linear potential, right? Okay? If the force is minus k, I take minus that, which is positive, and integrate, and I get kx. Okay? So this is the thing that's going to be acting on our U2 Daredevil. I don't know if you've seen it. I tried to find this particular video, and I was not successful. And I just thought of it this morning. I needed to have it, and I didn't. But there's no reason to put such a dangerous thing up on the screen in a nice peace-loving physics class. But still, let's think about what it is that this person, this crazy person thing, and I think I've set this one up so it's a linear force law. But here's the deal. Same curve that we had before, except it's not a curve. It was a straight line before, and it's a straight line now. Here comes the Daredevil from 30 meters. Okay, that's actually a little bit more than what they do. I think they've decided that they were anything above about 80 feet is getting to be very dangerous. But it's hard to imagine. But this Daredevil jumps off this horrendously high tower. I mean, it's taller than most of the buildings on this campus. And he goes through the air like this, straight down. And there's a swimming pool that's not too much bigger than just this little circle right here. It's about a meter high, full of water. And hits it belly first. Just bam, right in his face on. Tremendous fly of water, and the pool collapses. So a lot of energy gets dissipated over that 1 meter. So he's coming down from 30 meters, and then just 1 meter, the area here has to be the area here. He gains all this area, all this energy coming down, the little blue area right there. He's got to get rid of it in 1 meter. So he's experiencing 30 G. He's experiencing G all the way down, although experiencing that is weightless. You don't feel it. He's feeling some air, so he gets a little bit of energy out. Right? We're not including that here. And then, boom! He gets rid of it all in 1 meter. And gets up and high. I mean, wow. Well, obviously you work up. First you try at 1 meter, and then 2 meters, and 3 meters, and 4 meters. And I guess you build your tolerance up until finally you're doing 80 meters. And then at that point you decide you don't want to do any more. I've never heard of anybody go higher than 80. But 30 is about the limit that your body can really take. And this was discovered by not NASA, but NAC came before NASA, when they put Colonel Stapp in a rocket sled. And the colonel was all strapped in, and then they fired that rocket sled off, and then the rocket sled had big scoops, and it went in a lake and threw water thousands of feet into the air, and put almost 50 G on Colonel Stapp, and he survived. The trouble was, he didn't look very good afterwards. His face was completely black with bruises. His eyes were, sort of displaced, but then they were still work. And as far as I know, Colonel lived to a ripe old age. I haven't checked on Mr. Stapp. But 50 Gs, I believe 10 Gs is called one Stapp. So, and I don't know if you can imagine what 10 Gs are. You weigh 10 times what you do right now. And go by, multiply that by 5. So this is something that's been experimented with because, they were knowing that they were going to be someday doing space mechanics, and things go fast out there and you get decelerated fast. The Russians are the best at this because they land their spacecraft on land. We drop them in the ocean whenever possible. Okay, so the potential, this is the potential plot here. You lose the potential and then you get back to it. This would be assuming you didn't lose any energy in the process, so something's giving you some energy back that you've gone into the negative on, gone into debt with. All right, let's try a little bit more difficult one. And this one is particularly important because this is the one that describes virtually all of the motion that occurs at low energies and low laser flux when lasers come and start to oscillate molecules and atoms or solids. And the idea is that most things that are stable have a parabolic potential. That is, they have a quadratic potential. They have a force law that is at first linear. So here's one for a pretty hard ball coming in, and the idea is that the area under that, including a little bitty thing that's right there, should be equal to the area under the thing so that it stops. Same thing here. Okay, just a little bigger region right there. Looking at the potential plot, what we have is the thing comes down here and then basically runs into a parabola. That's the model that we'll be using for the Super Ball because it's pretty hard. It doesn't dent much. So the funny little stuff that's inside the parabola dip that you see more clearly here and very clearly here, I'm going to ask you to analyze a little bit of this in a problem, but I want you also to note right now the little red dash there, which traces where the minimum of the potential gravity plus force due to the crushing of the ball with this nice linear law. This is a balloon force law potential situation, pretty close to it anyway. And the bottom of the parabola follows a curve that looks like a parabola. So I want you to note that. That's something that will happen. And you see, every time you apply an electric field to a molecule, you're going to shift the center of charge a little bit, you see. It's called polarizability. The amount that it will move is related to the polarizability. So that electric field is linearly related to the shift of that charge until you put really high fields on it and it goes non-linear, and finally you can dissociate atoms and molecules. But before that happens, there's a lot of physics that just deals with the case where it's linear force law. And therefore an oscillator, a plasma oscillation, if you will. So these two cases that I've just given you are very important for physics. Now, the physics superball, as I said, is nonlinear. The general nonlinear force from the superball is the thing that we've been simulating here. So I'm turning to the back here. But this one, the bounce effects that we've been seeing so far that let us use the independent collision model to solve things that you would normally think you have to do some complicated algebra or differential equations to get. This one is taking advantage of the flatness of a nonlinear force law. And that's going to come up in the discussion of bouncing balls again, but this time as a parable, an amusing parable where I relate Los Alamos's cheap and practical seat-of-the-pants approach to problems. They're down in a beautiful desert on the side of a volcano called the Jemez Caldera, and that was used to be a ranch for summer camp and a school all year around, very private school for rich people, and beautiful area, beautiful, usually beautiful climate, especially in the summer, lots of lightning and beautiful skies. And then up in near the San Francisco area is a more politically savvy laboratory called Lawrence Livermore, near the town of Livermore. And their characteristics that I noticed when I worked at this one and then visited this one was that they were fancy and overpriced and very politically savvy. So these two labs sort of competed with each other. The other labs like Argonne and Hanford up in Washington, and there are a bunch of them in the East, and they're sort of out of this circuit. Most of the history of was between these two. They were the ones that were working on things that were considered very important. So let's suppose that this allegorical Los Alamos, which we call Rumpco, decides to do some work on superball bounce, which we all know about now, so we can understand that since they're seat of the pants, cheap and practical, they're going to do the calculation with ruler and compass like we have at the beginning. That means they have to have a little gap here in order to carry out this bounce. So this is going to come down, boom, boom, and pop up off of some heavy metal plate. Okay? So there's bang one and there's bang two, and they're independent. You've seen all this, right? We've been studying this. It's not on the board still, but I'll bring it up here to see. Now, Lawrence Livermore is much more sophisticated. Let's suppose that this is a slide they make of their work to go to the APS meeting. Well, Livermore is going to show up with much fancier slides. Their slides look like wedding invitations. And they've done the calculation with a force field. They have a computer that's better than a ruler and compass. The computer we've been using out here, which is in fact probably 10 times the power of the Cray that we had at Los Alamos at the time I was working there. That's a little bit humbling. It's that we have this room full of Crays here. $300 million or $1 billion computers that we're getting for a few $100s. That's very humbling. That's very something that really represents an amazing development in our work. Anyway, they don't need the gap. No initial gap needed. They can work with, they could even have a thing crushed into it and take off and bounce and do, they're completely free to make any sort of numerical experiment of this particular system. Well, what's really quite remarkable, and maybe TC, you might as well take advantage of the one of the incest, and that would be the nonlinear case. I'm going to see if I can locate it here. Linear two-ball collision, 1 to 7. Okay. Now, if I set this one up, that's not exactly what I want at the moment. I'm going to make it non-linear. The way I'm going to do that, I guess I have to go look for the original scenario and turn the gap off. Zero gap two-ball collision, 1 to 7.
Non-linear.
Yeah.
Change the 1 to 4.
And we have a potential drawing there showing it going. Okay. Now I'm going to turn the drawing off and replace it with a velocity plot. And that means going over here on this one and resetting plot V1 versus V2, which is very similar to what you've done, right?
Right.
And everything else the same. We have no acceleration of gravity in this particular thing, but we can turn it on later on. I want to keep it as much like the things that we have done so far. So here is this one, the crude old-fashioned thing, making a curve very much like that. And ending up, and I should have stopped mine before we had another bounce. I just want to do the throw and nothing more.
Okay.
So I'm going to make sure that it stops at the top.
Oh, I actually had it.
Right. I used to pause once at the top is what this one does, and that's the same as yours, I guess. And I'll do an animation and let it stop. So, kaboom, kabong. Now what's amazing is there's no gap. And the throw, 2.29, now they carry it out to a few more places here, right? That shows how smart they are. You students do the same thing. When they read the calculator, they got to write all 13 numbers down, right? And the final velocity here of the ball also 0.6 173 there. I've got a 27 here for some reason. But the main point is that this throw here is not that much different. 2.3 and 2.5. I didn't lose that much by getting rid of the gap. Okay? But in any case, Los Alamos says, look at Los Alamos, your theory is so crappy. You've got this thing that does this. This is what it really does. Your analysis is garbage. That would be a fair thing to say, right? This is what it does, right? Okay, so we get 2.3, we get 2.5, but that 2.5 was fortuitous. You're wrong. You've got to do this and forget your ruler and compass, go back to Greece or wherever you came from. Okay, that's the sort of arguments we would run into when something that was cheap and dirty, got the answer quickly, had a little bit of a what's going on here, but still, it's not quite right, you see. Now, you remember when we did the bounce with the 3-to-1 ratio? Worked pretty well when we did it with the actual Super Bowl. And now I remember we didn't videotape that, but maybe we should do it. Let's quickly do it, just to refresh the memory of that. Go ahead and swing the camera over. I'm going to try to do it right next to the Scotch tape holder there. Got to find the hole here, and I've got a brass pen that is, if I do it right, There we go. This is a 60-gram ball and a 20-gram brass pen that doesn't write. It's something I turned off on the lathe. But just watch this. I'm going to try to drop it as straight as I can. Except for a little bit of this bzzz at the end there, this ball lost it all, right?
No.
Okay? That's really, you'd think, very fortuitous that this model works in extreme cases pretty well. Okay?
But
All right.
what is the physical reason for that? Like, why is it that when we have a certain mass ratio, when the mass difference between two objects is large, the heavier mass comes to rest practically and transfers all its momentum and energy to the lighter mass? Why does it happen? Is there any reason?
Well, just remember, if you want to believe this theory, right, that if you draw a line from here to here, there's the bisector, right? The line going from there, which makes 1, 2, 3 to 1 ratio, right? Remember that?
Yeah.
So the geometry is telling us that should happen, that this would then be the center of a 3x1 square here that has a diagonal that ends with the velocity number 1, 0. All of the energy of this ball, essentially, except for a little vibration that we saw there, was gone. Sort of rolled away. And I better find that pen. If you see it anywhere, I'll get it. Oh, here it is. I've got it. It landed on this side this time. So that is fortuitous. Now, can either of these two allegorical laboratories explain that? Now, we've already talked about this, so this is a good review. Let's suppose they get together. And every once in a while they got together, and that was powerful, because these two different approaches tended to yield more insight than either one of them had. Because they were really doing things from completely different points of view, you might say. Okay? And let's suppose that instead of having a nonlinear force like y to the fourth, or even a quadratic y squared force, that we have a linear force, like this. Okay? And so that's what we'll simulate here real quickly. Here we are using the Livermore computer to do the job. So I'm going to set this up for the, and I've got to go get my initial conditions here. 7 to 1, 7 to 1. I forget now, I'm thinking, I haven't left the actual numbers.
Yeah, it should still be in.
Is it still there?
I think you just switched the exponent. And
Okay, here we go. This is the linear two-ball collision 7 to 1 ratio again of masses. But it looks the same until you look at the velocity plot and the result. Practically no throw, just now starting to separate a little bit. Isn't that amazing? What is going on? Now we can see what's going on. We can see that by making a linear force law, we don't have the flat region, which is equivalent to having a gap. In other words, Livermore had a gap. And if you make it linear, and presumably, and I've never gotten this to really work because balloons are weird shaped and stuff like that, but if you had perfectly spherical balloons, that's what you would have, is a Hooke's law, linear force law. And this is what would happen. The thing would come down, and the two would sink together, and then the two would separate together, more or less. And that's what we're seeing. That's what this is. almost no throw at all. So the flat part of a nonlinear force gives this explosive effect. So independent collision model is telling you the qualitative reason for this explosion, even though it doesn't have the three-figure accuracy that the Livermore type computing has. Okay, so you get a throw factor here of 3%, right? I mean, it's negligible, practically no throw for a linear force. Okay, and that completes the allegory for these two lefts. But you see, the thing I want you to be aware of is that this one, which we can do analytically, because we can do linear force laws analytically, is quite beautiful in a sense. And you remember, I discovered this thing completely accidentally because I took a pen and just used it as an indicator and I threw it into the ceiling and stuck it there. I was expecting this. Right? Well, why should they explode, right? There was no, it wasn't thinking, right? Okay, well, as I said before, when we just first mentioned the Super Bowl rockets, or whatever you want to call them, this was done at USC. I want to show you some stuff from the USC project and how that led to that sagittal potential analysis that I've been showing a little bit of already in the beginning of this lecture. So here's this paper that we wrote with I wanted to put all of the authors, all 23 of them, 22 students, up at the top. And it would have been the first paper of that kind. Now we have high energy papers that don't stop at 20. I think I've seen one that had 300 authors. It had more authors than there were words in the paper. So obviously the first, it had 250 words, so 250 of them got to write a word each. And then the other 50, I don't know what they did. Maybe they ran the experiment. But anyway, this is, very common to just put all the authors in a paper. American Journal of Physics wouldn't have it. So they did this weird thing. They said, class of William G. Harter. I think it's the only time it's ever been done. Because, all these guys contributed at some point in this thing. And it went through all of the pain and agony and then discovery that's associated with good research projects that occur at Los Alamos, Livermore, and all the universities that we pay our NSF grants to get. So anyway, these people are all doctors, dentists, and I followed some of them, and others have just disappeared from the scene. Maybe they'll come back after they see this video. But also I had some people working at NASA that helped provide various things that made the project easier. But this was actually done in the fall of 1968 and pretty well completed, but then there were some loose ends which I will describe. But I should point out that this effect since this time has not apparently we sort of owned this one. There are other people that did some things that were kind of like this, but actually making devices like this, we were the first, and this was completed, as I say, in '68. But since then, a lot of profs try it out. This is just one I picked out of the many that are on the web site. And it includes the unfortunate Harvard professor, Michael Tinkham, who's known for a book on group theory. So when I heard that this had happened, I was amazed.
What happened to Mr. Tinkham?
Yes, I'm still trying to find the video of what I call the Tinkham incident. But it is famous, almost as famous as the Varenzo, not the Varenzo, the such and such Narrows Bridge in Canada.
Tecumseh.
is it Tecumseh?
I thought.
Tacoma.
Tacoma Narrows.
Tacoma, that's it. Tacoma, Washington, right? That bridge video, you've all seen it, resonance, right? Well, a weird kind of resonance. That's the trouble. It's very poorly taught what really happened. But this one, I'm going to find it eventually because I know people that know about this. Anyway, what Mr. Tinkham did was basically shown on this video, and you can see it almost happened to this professor if you go and get this video and run it. And here's the full address which you can plug in, I think, and get that thing, or else just Google the Walter Lewin at MIT, okay, which is across the river from Harvard. But what he did here is he takes a basketball, holds it in one hand, and he's got a tennis ball in the other, and he just lets it go. Okay, and the tennis ball goes to the top of the lecture hall, first sort of deviantly, and then he does a pretty straight one. So he is skilled at doing this. But when Michael Tinkham did it, he tried it out beforehand. Wow, that's neat, I better show the students. And he did it with a golf ball, okay, which went even faster. But this one didn't go to the ceiling, it hit him in the balls. He doubled up, and that was the end of the class. And this is on video, so I just got to, you've got to tell me if you find it, and I haven't found it by the time that you see me again. But that's the, basically as far as most people take this. But of course, we took it to the point of building, and this is what started the whole project. The Calvin Gray built this, just brought it to class. He got a bunch of stuff out of the lab, catched together 2 magnets with some wires, and another one that was on the end of that came down, and then a rubber band. This was just a rubber band. But we used that thing to do a very precise drop of the super balls, which all of them had a protective case. They weren't just pens. They had little protectors so that the balls didn't get shattered after multiple collisions. So this was a very sophisticated experiment that came up, and the goal was to explain things like that with 3 or 4 as opposed to just 2 balls. This model kind of worked, but it would tear itself apart. This works very well. Okay, so I want to show you the story of this. This is the visit to Whammo manufacturing and a little bit of the results of this so-called Project Ball. After this thing started, after the initial, shall we say, probably about 2 weeks of this, somebody told somebody at NBC about it, and Ray Duncan Reports put it on the 6 o'clock news. So the whole Los Angeles Valley heard about this, including everybody at USC. And the USC mechanical engineer said, oh wow, I bet we can help with that. And they had this new tensometer that would plot out the force curves for various things. Super Ball, no problem. And so they got us the force curve so we could do a Livermore style calculation that involves solving a differential equation of a motion. And they gave us also access to their analog computer, which we could program to solve the differential equation. Now, that's very different from using a digital computer. And at that time, analog computers were in every engineering building, and the digital computers hadn't gotten to the point where it was convenient to solve differential equations unless you had a zillion dollars and could get one from places like Los Alamos. So, big splash. Everybody in the campus said, oh, look at those guys, they're working on Project Ball. Of course, that was funny. Everybody thought that was funny. This is the 60s, you gotta realize. And after the initial glow of publicity, things began deteriorating in old physics room 69. That's the Project Ball room, which is in the basement of a building that really should have been torn down, but and is now, of course, torn down. USC is a palace compared to what it was then. First of all, the fancy pants computer theory that was made possible by mechanical engineers did not jive with that drop tower experiment. When you do it very carefully, it was clearly off. Also, the USC Building and Grounds decided that room 69 and all the rooms around it actually needed painting, and they did. And so they kicked us out for a week. Okay? So this is what research is. You know, you start out and you get an idea and it sort of works, and then, oh crap, it doesn't work at all. You know, what am I going to tell these students? You know, if you really push physics, it will show you it doesn't work. I mean, what kind of message is that? But it's true. It happens. You go all onto something, and you're all excited about it, and then you hit some walls, right? Some big walls, some little walls, you trip, blah, blah, blah. Well, that's where we were. You know, the course is going on. This is stuff that's, you know, just a part of the course, but, you know, I was hoping to get it all cleaned up, you know, early in the course, but we didn't. We just kept going. So I had to do something. So when they came down, they're doing this for the lab, you see. So when they came down, I said, you know, what do you think about going down to visit Whammo? And maybe we all get, you know, them interested in something that they would actually sell, and we could make some money. Wow, right? So I called them up, and they said, hey, that sounds good. Come on down. Yeah, we could make something out of that. You know, so invited us to visit. Yay, big dollars, dollar signs and eyes, right? Well, it's a big switch from here where everything was crap. So days later, finally got a car convoy together, and we drove down to San Gabriel. It was down San Bernardino Freeway, a little bit to the east. It took about half an hour to get there. And happens that was the alpha wave day for the inventors of the San Gabriel. By the time we got this thing straightened, they were all doing alpha waves for the day. And that was supposed to increase their creativity. I don't know if you heard about this, but California has a lot of fads, and this is one of them. You can read, electroencephalogram, you can read your alpha oscillations if you put the contacts in the right place, and you can actually think about getting them bigger. You can, you know, now they do this sort of stuff. You can actually move cursors with your brain at the MIT labs now.
So what does it do, Dr. Harter? Like measuring your alpha wave, what does it achieve?
Well, I never tried it. But people that do it claim, and it's almost lost in the noise, but they claim that if they thought real much, they could increase the alpha wave. And this was supposed to increase your creativity. This was supposed to help you solve problems or invent new things, and that's, of course, what Whammo was all about, is coming up with the next big fad. And so the idea was you do the alpha wave thing once a week, and maybe it would increase the number of inventions, and, of course, the bottom line of the Whammo Manufacturing Company, which already had some really great successes. The hula hoop was worldwide, right? The Super Bowl, also pretty much worldwide. And then they have a bunch of other things. So, they weren't available, these guys that were so enthusiastic. All we could do was, we were greeted by the general counsel. This guy was the lawyer for the, and part owner of the corporation. So he's a more down-to-earth person, worried about the things, and he says right away that this invention is too dangerous. End of story. It's just too dangerous. And you have to agree, a pen, you know, going up and sticking in your field, what if it sticks in your eye, right? Now, when I showed this to Feynman, his suggestion was a dartboard on the ceiling, right? That's not in the direction that this guy was talking. Afterwards, I thought of a Nerf space shuttle, you know, that wouldn't hurt if it hit you, and, you know, it would go up, and maybe it would be made out of very light material and could fly around afterwards. We still haven't built it. I think we could do that. But at this point, we were just bombed. bummer, bummer, bummer. Where's all the money that we were thinking about? No dollars. Okay? But he looked at us and he realized we were pretty sad. So he offers boxes of super balls, many sizes, just collected from various experiments. They were sort of cluttering up something. So everybody got a box of super balls and other shapes. They had icosahedrons, they had octahedrons, they had cubes, you name it. And balls this big. I had a couple balls that were really big. So, you know, if we're going to continue the project, I figured, well, hell, let's take it. So, we're still a little sad, but we got to go back to room 69. And by that time, painters had left, but the paint was still wet. So I said, well, let's just put the stuff here and we can come back and work on it later. And somebody dropped a box of balls and were bouncing all over the place and got in the paint and left little spots on the floor. The rest is history. The little paint spots on the floor show what was wrong with our fancy pants computer theory. And you know the answer. The engineering curves are isothermal. You slowly squeeze on the thing and keep reading, right? We needed that. These force curves have to be made quickly. How do you do that? You measure the spot size of a drop super ball from different heights. Put a little dye on it so it leaves a circle. So we made a lot of little dots. You drop just a little bit, you get a little dot. Drop a bigger one, you get a bigger dot. And use the Sagittal theorem, x equals d squared over 2r, to figure out what your x is versus your height. So that gives you an energy curve. And then you take the slope of that, and you've got your force curve. And you do two of them. By first do the regular drop, and then you play around, sort of fake the one where the two balls come together, making an average. That was a little squirrely, but we got that right finally too. So the idea was that you could get the results of the experiment. That's the error bar stuff here. And we even took it down where the ball had to bounce twice. And of course that didn't fit. But this part right here fit really well. So we got out of our trouble. We got out of trouble by doing this. And now we could take on the multiple bounce objects. So we could do predictions for them and then do experiments on that. And that kind of ends the paper with that. Okay? So I want to just quickly show you a couple of these things in some detail. I'm also going to give you a problem to do the geometry for this. So I want you to study this page fairly carefully, because it starts off with one bang, okay? So that takes care of the M1 and M2 just like we've always done. But then you do the second stage. Remember, there's a 45-degree line here that holds the center of momentum for the first two. To get the next collision between number 2 and number 3, you simply take your line across to 45, bring it down, okay, to here, and now you have this ball coming down with the same velocity that number 2 is coming down when it collided with the upgoing thing. This one's going to collide with the velocity that we just gave it. So now you do a line here with a slope ratio, in this case 30 to 10, if it's these two right here, okay, 3 to 1 slope ratio there with a negative sign. This one was 130, that's these two together, okay, so you have two different sloping lines, but it's going to have its center of momentum right there, and there's the final blast right there. You see, we were limited before by 3. This thing blasts right through that without any trouble. So that's the thing I want to show you. This is the independent collision model. Here's the actual thing with a quartic force law. Here's the thing with a linear force law. It doesn't throw much at all, just like we saw with two balls. Okay, so that's kind of cool right there. And we should point out there's an analogy here between the Super Bowl towers and acoustic horns. The difference is that we start with something that's big and slow and get something that's small and fast when we shoot the balls out. But run that backwards, you see, you've got a trumpet, you go into the trumpet, so you have some little thing going very fast, vibrating very fast, right? And you can, as they say, impedance match between those two and make the big thing come out going very slowly. That's a lot of air moving with a slope. The other analogy, of course, is tsunamis. As the beach changes, the depth of the water, you see, if it does it gradually, which this is kind of doing, if it does it gradually, then this wave is going several thousand miles per hour with a height of about that from the shock of the earthquake, okay, comes to the beach, it starts to slow down and build up amplitude, okay? And of course, if you're on the beach, you've got a wall of water coming at you. That's the tsunami of the classical variety, which we've heard a lot about in the last 10 or so years. I'm going to give you a problem that just asks you to find the optimum mass, M2, for 3, given these masses, and do it algebraically. You can check it with geometry and an independent thing as well, but that's what I want you to do. This is an independent collision model. I'll give that to you later on. Okay, finally, the very amusing and colorful story of Sterling Colgate, who independently discovers these towers 20 years later and patents in 91, I think. I'll show you the patent. But anyway, here's what Sterling Colgate was physically interested in and became something of a originator of a model, very simple model, for a core collapse supernova. Now the big ones that we're talking about today have all sorts of other things happening, and their masses are billions of solar. This is only a few thousand. Or maybe, this one is actually only 25 sun masses. Yeah.
Is it the same gentleman who owns the corporate? Is Sterling Colgate the same person who owns that company, Palmolive Corporation?
Yeah.
The Colgate.
Well, he is part of a family,
Okay.
but he was rich. He didn't have to work at anything.
Okay. So is he a physicist?
Yeah. And I know him from a completely different thing. My ex-wife, Margot, went to Colorado College with his daughter, and they were friends. So I knew a little bit, but I never met him. He was very cantankerous. I never tried to meet him, actually. I think I would have maybe gotten along famously with him. But this is a picture of a supernova, and the idea, and this is in Science magazine, and there's the authors right there. You can Google their original research or just pull this thing up. The basic idea is that it cooks and cooks and cooks its elements, starting with hydrogen, then making some helium, and then using the helium to make some carbon and oxygen, and then the carbon goes together to make neon. And these durations of time, it takes 10 million years to do that. Then in just a million years it starts to put the carbon and oxygen out. And then in 1,000 years it's managed to come up with neon, sodium, magnesium, and aluminum. And it only takes 3 years to get some oxygen. I mean, this is the kind of nuclear physics that he went through with Chandrasekhar to come up with this model. A bunch of other people worked on it too, I think. And finally, you get to the end of any possible nuclide chain that you can think of. The production of iron, I believe 57, is the end of the road here. And that only takes a few days. I mean, it takes a few months to finish the silicon, argon, calcium part of this thing. So what you've got is a stacked up tower of superballs here.
So just a question on this one, on this chart. So when you get iron, I mean, as a product of fusion,
when you run out of stuff to generate a hydrogen bomb, basically a hydrogen helium, carbon, neon, oxygen, silicon bomb, right? This is what's going off to keep this thing, suspended. This thing that's only 25 solar masses. So, here's our sun. This thing is, probably about that big compared to our sun, right? And it's all suspended by this horrendous things that's keeping the sun the radius it is, right? Then all of a sudden, it goes out.
So when iron is formed, will it be a molten or a gaseous state? Like, what would be
Oh gosh.
does it have anything?
It's under so much pressure.
So just like atoms.
It's in a state that we don't even know,
Oh, okay.
right? I mean, just think of the pressure and temperature
That's right.
that you've got there, okay? But the point is that it ain't supporting the whole thing anymore.
Okay.
It's not gassing out, right?
Right.
This thing is coming down, right? So it's like a tower of super balls coming down, right? Except they're coming down from all directions, right? And that's this picture right here. Shockwave, boom! That's your supernova model that these guys came up with. And we owe a lot to this little super ball experiment. We are, as Carl Sagan liked to say, made of blown up stars. And this is just one model. The newer models are much more complicated than this. But the thing that happens here is we get more elements on the way out. The energy that you actually have released in these is 100 times that which our sun, our little measly 1/25th of this sun, will put out in its entire lifetime.
What fraction? 1.1?
This thing does in 10 seconds.
Oh, okay.
In 10 seconds it puts out our sun's lifetime energy times 100. Now 99% of that energy goes out as neutrinos.
When a supernova explodes,
The 1% is the total sun solar output. It comes out in other things. Particles and elements and atoms and us, stuff we're made out of. Okay? On the way out of that horrendous blast, you make a whole bunch of other elements. Now that isn't clear, but apparently the actinides, the plutonium, well not plutonium probably, but maybe plutonium. But anyway, all the stuff that's at the bottom of the periodic chart and stuff that we've left out in the middle gets produced on the way out according to,
so you mean to say,
how much do you believe, right?
so according to this theory, the elements that we see in the periodic table are produced
In blowing up stars.
Yeah,
Because you start with hydrogen.
Yeah, that's
Start protons, right? And electrons. Like, yeah, the cosmology is a real fairy story. It's not as bad as some of the religious documents that claim to tell you what happens. But this one we can actually get numbers from. Now here's Sterling. He's got a really neat middle name, Ochtendklaus. So he's Sterling A. Colgate, or just Sterling. And very, nice looking gentleman, sort of devilish looking, and he was a devil in many, just a real cut up, you might say. He sort of out Feynman's Feynman in many ways. Now you got to realize another thing. He went to the school that got displaced by the Manhattan Project. He was just a little kid when that happened, but it made him decide that he wanted to be part of that, whatever was going there, and nobody really knew what was going there. So he ended up at Los Alamos and Livermore, very seldom at Los Alamos, but close to Los Alamos because he became president of New Mexico Institute of Mining and Technology. And did lots of stuff while he was there, like try to throw dynamite at a tornado, I think was one, or else hang sticks of dynamite in the air and try to duplicate the thunder that you get from a lightning bolt. And he had, all sorts of sophisticated instruments to record that, okay? And his quote, "I was always enamored with explosives, and eventually I graduated to dynamite, and then nuclear bombs." He helped Teller and whatnot do the hydrogen bomb. So, you know, what a history this guy has. And I'm using off-color aside, and I'll let the cameras run for this one. He had genital herpes, and he had a relationship with a student at New Mexico Tech, and she sued. She sued him, and his defense was that he had told her that he had this. And they find, I don't know what they did, they probably made him pay some money or something, but the Board of Regents of this New Mexico Tech fired him from being president. And so he wrote a letter of resignation, which, you know, you'd expect somebody to do if they were threatening with fire. The problem was that the Xerox machines, you know, the big Xerox machines they had then, you know, that had a nice glass plate, he proceeded to make a watermark for the letter of resignation, which he took his pants down and sat on the Xerox machine, and his anal pour. So, you know, that's just, you know, a very childish thing, right? But I think the Board of Regents deserve it. They really should have fired somebody this talented. But here's our patent. In 1991, that's the filing date. The priority date is same. Okay. This was with those fellows here still. Colgate was the real driver behind the thing. Okay. And this is the actual product. You can get this still. And I've been meaning to get another one. $9.95 then, it's probably more now. But you'll notice something in the package. You see something in the package beside the Tower of Super Balls? Safety glasses.
Yeah.
That's what we should have said to Laura. I said, well, we'll put safety glasses in it. Yeah. So that's the only original thing that he contributed to this. Because, you know, here's our thing. And his claim, the claim that let him have a patent, was the constraining element is an interior guide pin in which the remaining balls can slide freely. There was a 73 proposal or patent that just had the balls somehow mysteriously attached. You were supposed to pile them up like Professor Tinkham. So his is the idea, you know, of course this is happening in 1971, or actually 3 years before that. And now, of course, I have to pay for the APS to get my own paper. I didn't though. We went through the library, so I didn't actually have to pay the $30 for paper. But anyway, that's the history of the Super Bowl. Now, there's some more history too. This country has something called the buckboard, the Western buckboard. The roads are terrible, full of rocks and gullies and potholes and whatnot. They're dirt roads with rocks in them. How do you stand to ride a wagon that's going pretty fast? You've got a team of horses. Okay, you want to go fast. This is Oklahoma, Kansas, Iowa, Arkansas, but Arkansas is kind of hilly, so not so many of these. What do you do? Okay, you ride on this thing with a spring under the seat. Okay? Well, what's that a model for? It's a model for disaster. This was a deadly instrument. It didn't have seatbelts, but they needed them. So it is a terrible, terrible reputation. You get bucked off quite often. Okay, now all of this is in the textbook. The falling column of balls, you can do the animations yourself. It's really quite spectacular to have a column of balls come down and then go back out again. And TC is going to start one of those. So these are generalizations of this device right here. And remember, The only reason that thing works at all is because it's approximated by the independent collision model. And it is approximating that even though they're touching each other, because it's a nonlinear force and has a flat gap. So there's your classic ball thing there. And it will not work if you use a linear force. If you make a linear force out of that thing, it's a mess. See, it looks the same, just like this looked the same, but look what happens.
It's actually a 4-ball collision there for a moment.
Yeah, yeah. You only see the first two being plotted in this case. So, if in fact the ball's potential, effective potential, was a linear one, a Cook's law, you know, our favorite potential in the physics business, right? If it was that, we would never sell this device. It does what you'd expect. It would just, you bring it out and it would just go, you know, they just do that, right? That might be amusing for a while. Actually, the minute it becomes fairly amusing, as you can see right there. But it would not do the wonderful deals where you could take two, the other two pop out. You see. Now, it would be nice to have it set up so you could see various other things like that. But this is a single pop-up that that thing is famous for. Now here is a typical example of geometry being used to do 4, and that's the most we ever made. Sterling's device has 5, but his mass ratios are not the best. You can do a lot better, and you can see from this how to do that. So, you know, that device can be improved. Now I also want to show here the zigzag geometry associated with inelastic collisions, like freeway crashes. And I believe there are some running on this. They're not spectacular because basically we've turned the damping up enough so these cars crunch. So they're all totally inelastic. But here comes this car speeding, and we've got 5 stationary cars parked in the fog on a California freeway. And you've heard stories of